So in this video, we're going to discuss the two cases, that are often found in engineering systems. You have a case where you have your stress element or your body is under a case of plane strain versus plane stress. All right. So for plane strain, it occurs when if you have a very thin part, so if the thickness of the body is very, very small relative to the other dimensions of the part, or relative to the parallel plane in the parts, right? And if you have also that the stresses along the positive direction or along the z direction are equal to zero, in this case you can say that because of that, you can say that the stresses along the z-axis would be equal to zero in this case, right? So, all right, for plane strain, it's like the opposite case. So if the thickness of your part is very large relative to the other dimensions in the parallel planes, then the strains in the thickness direction can be assumed to be zero. So in that case, our strains along the z direction are going to be zero. So epsilon z, gamma z, yz, and gamma zx are going to be zero. All right. So in both of these cases, the loads are not applied along the z-axis and can't vary as a function of the z direction. And then we can also say, so for these two cases, we can simplify our equilibrium and compatibility equations down to a single equation. So we're going to combine our equilibrium equations and our compatibility equations. So in so we were given our two equilibrium conditions, and then we were given so these are our equilibrium conditions, and we were given our compatibility case for a plane. We could define using this one term here. So we're going to try to simplify for both these two cases of plane stress and plane strain. We're going to try to combine these sets of three equations into a single equation that can determine whether or not our state of stress will satisfy our equilibrium and compatibility equations. So for plane stress, here are our equations that relate our stresses and our strains together. So if we use our equilibrium, the equilibrium equations on the last page, we can rearrange them to solve for. We can take the derivative of our equation with respect to x for the first compatibility equation, and then the second equilibrium equation we'll take the derivative with respect to y, and we'll solve them both in terms of dt d tau x dy. So we can add them both together, and we end up getting this as our final equation here. So if we plug in our stress-strain relationships into the compatibility equation that we had on the last page, so this equation here, if we plug it in, what we end up getting is we get these as our new compatibility equation. So what you can see here is that we can then plug in this equation here to get rid of our tau of xy terms. We end up getting this simplified equation here. All right, and then we can simplify it down a little bit further if we use the Laplacian operator, where the Laplacian is just the derivative of your variable with respect to x plus the derivative of your variable with respect to y. Okay, so if you square it, it just ends up being, the Laplacian squared ends up just being the second derivative with respect to x plus the second partial derivative with respect to y of your variable. Okay, so you end up getting this equation. In a similar fashion, you can do the same thing for your plane strain case. So if you do that for plane strain, what you end up getting is again, we have our stress-strain relationships here. What you end up getting is you can if you end up doing the same process where you take the equilibrium equations and the compatibility equations and you plug them all in and substitute them in for each other, what you end up getting is you end up getting this equation for the plane state of stress. Okay, so if this is found to be true for both the plane stress and the plane strain equations, what this means is that your state of stress, your stress, and therefore your strain is compatible, and your stress element is in equilibrium. Alright, so that's the big takeaways. So if you have a case of plane stress or a case of plane strain, you can evaluate both your equilibrium and compatibility equations using these two equations. Okay, you can, if you have only one of the equations, you can convert between the plane stress equation to the plane strain equation, or from the plane stress equation to the plane strain equation to the plane stress using these substitutions. And then from a materials perspective, if you have a very thick component and you have the stresses are going against, or I guess normal to that thickness, for the same plane strain will result in higher stresses compared to the same element if the material was allowed to deform along the z-axis. Okay, so typically very thin components relative to their size are very strong because they're not as restricted.